Have you ever just been stopped in your tracks by, well, by nature doing something totally unexpected, almost unbelievable?
Oh, absolutely. It happens.
Well, today we're doing a deep dive into one of those wild things,
Yeah.
rogue waves. Those massive waves that seem to appear from nowhere.
Exactly. We've really been digging into this rogue wave study guide, trying to pull out the key stuff for you.
Right. The mission today is basically to get a solid understanding of these uh, really fascinating and honestly pretty dangerous phenomena.
No fluff, just the essentials. And important to say up front,
Yeah.
these aren't tsunamis. People sometimes mix them up.
Good point. Yeah. Not caused by earthquakes or anything like that.
Yeah.
Rogue waves are, well, they're their own thing entirely.
Precisely. Tsunamis are more like these long, fast surges, right?
Really?
But waves are different. Think sheer walls of water.
So what actually defines a rogue wave then? According to the guide, uh, it's got to be at least twice the height of the waves around it.
Yeah, twice the significant wave height, technically.
Yeah.
And they're incredibly steep, like a cliff.
And they don't hang around long.
Nope, very short-lived. And interestingly, they can pop up in the deep ocean or closer to the coast. It's not just a deep water thing.
Okay. But the really unnerving part is how unpredictable they are, isn't it?
That's the core issue. Your standard weather and wave forecasts, they just don't typically see these coming.
Which makes them so dangerous. So, okay, why do they happen? The guide lays out a few scientific ideas.
Yeah, there are a few main theories scientists are working with. The first one is constructive interference.
Right. Explain that a bit.
Well, imagine you have several different sets of waves, maybe coming from different directions, different storms,
Okay.
and just by chance, their peaks all line up at the exact same place at the exact same time.
Oh, so they add up.
Exactly. Their energy combines just for a moment, creating one freakishly large wave. It's like a temporary energy spike.
Like a flash mob of wave energy, sort of. Okay.
Mhm.
Then there's the idea about ocean currents. The Gulas current is mentioned.
Yes, strong currents can really play a role. Think of a current flowing against the direction the waves are traveling.
Okay, what happens then?
The current can sort of squeeze the waves together. It shortens the wavelength and focuses the energy, making the waves steeper and taller.
Like hitting a wall almost.
A bit like that, yeah. Or waves meeting opposing swells can have a similar effect. They just pile up.
The guide also gets into something called nonlinear wave theory. Sounds complicated. Modulation instability.
It does sound technical, but the basic idea is pretty interesting. It suggests that within a seemingly normal group of waves, energy isn't always stable. It can sometimes spontaneously transfer and concentrate into just one wave in that group.
So one wave basically steals energy from its neighbors.
Kind of, yeah. It grows really rapidly at the expense of the others. It's a bit counterintuitive, but the math, like the nonlinear Schrodinger equation, supports it.
Okay, theories are one thing, but how we actually seen these?
Mhm.
Measured them. The guide mentioned some real cases.
Oh, absolutely. This isn't just theory or old sailor stories anymore. The big one was the Dropner wave.
In the North Sea, right, 1995.
That's the one. Measured precisely by instruments on the Dropner oil platform. It was 25.6 meters high. That's about 84 feet.
84 feet, that's huge.
Confirmed. And the same year, the cruise ship Queen Elizabeth II hit a monster estimated at 29 meters, 95 feet, during Hurricane Lewis.
Wow.
And then there was the Andrea wave in 2007, another confirmed event. So yes, they are very real.
Okay, so if they're real but hard to predict, how are we detecting them now? How did we measure the Dropner one?
Well, we have better tools now. Special wave buoys that measure wave height, definitely. Also radar systems, both ship-based and satellite altimeters looking down from space. And sensors on offshore structures like that oil platform.
But prediction is still the tricky part. The guide emphasizes that.
It really is. It's tough because the conditions that create them seem rare and complex, but there's progress. Scientists are using things like AI models, machine learning, feeding them vast amounts of ocean data to try and spot patterns, precursors.
Trying to learn the warning signs.
Exactly. Statistical studies, too. It's like chipping away at the problem. We're getting better at identifying the conditions where they might be more likely.
And understanding this isn't just academic curiosity, is it? There are major real-world reasons.
Absolutely critical. Think about safety. Giant ships, massive oil rigs, offshore wind farms. These waves pose a huge threat.
Yeah, a direct danger.
So understanding them helps design safer ships, build stronger platforms, and crucially, improve marine weather forecasting to give better warnings. It saves lives and prevents environmental disasters.
Okay, so wrapping this up then. Rogue waves. They're these immense sudden waves, much bigger than anything around them,
Yep, steep, short-lived, and hard to predict.
caused by possibly a few things working together, waves adding up, currents focusing them, or this weird energy transfer within wave groups.
A real danger out there, but science is definitely making headway in understanding and detecting them.
We're getting a better picture all the time.
We are. And it really makes you think, doesn't it? The Dropner wave was only properly confirmed in 1995. That's pretty recent, geologically speaking.
Yeah, true.
So, what other, maybe equally surprising or powerful things are still happening out there in the oceans that we haven't quite grasped or even discovered yet? And what could finding them mean?